So now we're going to go ahead and get started with our discussion on section 12.4, which is dealing with the normal distribution. Okay. Now, normal distribution is a common name for it. Another way you might see it written is called the bell curve because of its shape. It's also sometimes called the Gaussian or Gaussian distribution, named after Carl Friedrich Gauss, who was a prominent mathematician and physicist. So our normal distribution is a distribution that looks something like this, where this is our line. So it's just a little bit above this line here. Now, a few things. The area under the curve in total is 1, much like our basic probability functions. Okay, so if we're looking at just general percentages that lie under the curve, 100% is under the curve. The other thing is that our median here, our mean equals our median equals our mode. Okay? So the mean is just our average, the median is the middlemost entry, and the mode is the most common entry. In a normal distribution, we see that this is the case. Okay? Some other properties about the normal distribution, and the most noteworthy one is what is called it's called one of two names. One is the empirical rule, and the other is the 68, 95, 99, 7. And what this rule states is that if you start down at your mean, x bar, and you look, and you go over plus a standard deviation, or minus a standard deviation, the total percentage of the curve that lies between this one standard deviation, 68%. So 68% of your curve lies in this region here. Then if we go down another standard deviation, so we're at minus 2 sigma, and we go up another one to 2 sigma, the total area under this curve, or this part of the curve, it's 95% of the total amount. Then if we go even further to 3 sigma and negative 3 sigma, then we have 99.7% of the curve. Right? So if we start at x bar and go 1 above or 1 below, we have 68%. If we go 2 above or 2 below in terms of standard deviations, we have 95%. 3 above, 3 below gives us 99.7%. Now, we can break this up a little further if we so desire. So if we note that there is 68% in this total amount within one standard deviation, and this is our x bar, then we note that the area for either side, just from our mean to one standard deviation, this would then be 34%. Then if we go another standard deviation above or below, so now we have our 2 standard deviations, so we know that this whole thing here is 95%. And since this region is 68% and this region is 95%, then we see that these two regions make up a grand total of 27%. Because 68 plus 27 is 95. So that means this region in particular here is 13.5%. Then this region here is another 13.5%. And if you go even further with our third, we'll note that, of course, within 3 standard deviations, deviations, we have our 99.7%. So since we have 99.7 in there, then that means that, well, this region here and this region here, if we put those together, those will represent a grand total of 4.7%, or each of those individually will give us 2.35%. Okay. So that's just our breakdown of our standard deviations. Now you can find each of these individual regions if you just remember this empirical rule. So within plus or minus 1 standard deviation, 68%, plus or minus 2 standard deviations, 95%, plus or minus 3 standard deviations, 99.7%. So now, let's go ahead and just take a look at some examples here. Okay? So let's start by taking a look at number 2 on page 819. Number 2 says the test scores on a test are normally distributed with a mean of 100, standard deviation of 20. Okay? So we know our x bar, or our mean here, is going to be 100, and our standard deviation, or sigma, that is going to be 20. Okay? We want to know 2 standard deviations above the mean, so it's 100 plus 2 times 20, or 100 plus 40, or just 140. Okay? So you just take, since it's 2 standard deviations, just 2 times the number of, or times the size of each standard deviation. That will tell you yours. Nothing too bad there. Number 4 says, well, what about 1.5 standard deviations above the mean? Same thing, we're just going to have 100 plus 1.5 times 20. And 1.5 times 20 is 30, so we have 100 plus 30 is 130. Number 6, 1 standard deviation below the mean. So instead of adding our standard deviation, we're going to subtract that standard deviation. So these are pretty straightforward here. Nothing too revolutionary on any of these. Now if you want to pause and look at any of this, feel free to do so now, so I'm going to delete what I have here. So now, let's go ahead and take a look at, say, problem number 12. Now it says use the 68, 95, 99, 7 rule. Okay? So it tells us here, it shows us that in the middle we have 17,000. So that tells us x bar, or mean, 17,000. Then our next indication here is at 17,500, which is 1 standard deviation above the means. That tells us that sigma is 500. Okay. So we have those 2 pieces of information, and they give us a little bit more on that chart. So number 12 is figure out how many are between 16,000 and 18,000. Well, 16,000, you'll note, well, that's 1,000 less than 1,700. Now, since it's 1,000 less than that, that tells us it's 2 standard deviations below. So 16,000 is 2 sigma, or is negative 2 sigma. Okay? So it's 2 standard deviations below. And then we want to go up to 18,000. So 18,000 is our x bar plus 2 sigma. Okay. So now we are within plus or minus 2 standard deviations. Well, since it's 2 standard deviations, we use our empirical rule, which is 68, 95, 99, 7. So this tells us that we have 95% in the region of 2 standard deviations. That's how we got number 12. So then, let's go ahead and move on to, say, number 14. This says between 17,000 and 18,000. So if we're looking at 17,000 and 18,000, well, the thing to note here is that 18,000 is 2 standard deviations above the mean. So let me just go ahead. So between 17,000 to 18,000. So this is, we want to know what percentage of our data lie in this area. Okay. So we'll note that we start at our mean, and then we go to 18,000. Well, 18,000 is 1,000 more than our mean. And since our standard deviation is 500, this tells us that it's plus 2 sigma. Now, if it were plus or minus, it would be a total of 95%. Okay? But unfortunately, we just have the plus 2 sigma, so that means that it is going to be half of that value. Okay? So instead of the full 2 sigma, it's half of that, which gives us 47.5%. So that's all we're doing here, simply noting how much above or below our standard deviation we are. Hopefully these are not too bad. The next part we want to mention are the concept of z-scores. Now what z-scores are, they're ways of us to convert data into a particular representation in terms of the number of standard deviations. Okay? So the z-score of a given data point is x minus x bar over sigma. Okay? And this will tell us how many standard deviations above or below the mean it is. Okay? So let's go ahead and take a look, say, at number 34. Number 34 says a set of data items is normally distributed. So when they say normally distributed, that tells us it's a normal distribution, so we can use our empirical rule. Normally distributed with a mean of 60 and a standard deviation of 8. In exercises 33 through 48, convert each data item to a z-score. So we have 76, and we want to convert that into a z-score. So we're going to take our 76 minus our mean, which is 60, divided by our standard deviation, which is 8. Okay. This will tell us our z-score. Okay. So 76 minus 60, that's just 16, over 8, 16 over 8, it's just 2. So, and this is the way that we write this, z sub 76, or the z-score corresponding to the data point of 76 is 2. So this is 2 standard deviations above the mean. Okay? Now the video is running a little long, so what I'm going to do is finish it here, and then I'll take a look at some more examples in the next one.